Hello everyone, it is December 10th, 2024, and this is the bi-weekly libhal meeting. Alright, for the agenda for today, we have quite a few items. So a couple of these items were from 2 weeks ago when I talked about a couple of the new things that'll come into libhal 5.0, but I did make a couple of changes. But the first thing I'll talk about is the libhal organization page and some fixes I made to Clean Tidy. Then we'll start going through the list of all of the changes that will happen in libhal 5.0. Again, things are still variable, things could change, but for the most part, these are some of the rationales and design ideas we have. All right, so first, when you go to the organization page for libhal, the front page was pretty empty. And one of the pages that I actually use quite often is the project info page on the libhal GitHub IO page. So there I can look at all the projects and see where if they're passing, if they're failing, and what their latest versions were. Now that particular spot is just kind of out of the way. It's quite a few clicks to get there, and most people I think will forget. Whereas github.com/libhal is relatively quick and easy to get to. And I thought that this would be a really good place to show a lot of this information. At some point, I expect that we would have some sort of directory, some sort of system that allows you to type in the types of drivers that you want, and then it will tell you where you can find it in one of these packages or in some other external packages. Because we'll probably continue to grow this as time goes on. The device drivers should be limited. But as we add things for different platforms and expand in that way, we might see more need for a directory. But yeah, this is what we have now. I think it's pretty useful. Oh, and then I'll talk about this in a sec, but yeah, everything is failing right now, and that's because I've re-enabled some checks that really should have been there in the first place, which brings us to the next slide. So I fixed Clang Tidy and CI. On top of this, I've also added in a couple of additional targets just because I can and because it's a good idea. I found that the instructions for setting up LLVM, literally the directories, I think the directories are the same between Mac 14 and 15, but Mac 13 is slightly different, I think. Or they could all be different. I forget. But basically, there's a difference between where they're located, and I need to account for those in not only the targets themselves, but also in the profiles, basically the profiles for your host. And I think that might have been some of the reasons why some Mac users were having problems. They would go through all the steps, and nothing would really work. And then what I would end up doing was like figuring out where their LLVM instance is, and then um, um, from there, link it into their path so that their code can actually find it, and then that works from there. But I think this is going to resolve those issues we had before. And then also there were some slight differences in Ubuntu 2024, so I made sure to support that as well. So yeah, I got Clang Tidy to basically be installed properly in the test.yaml file. It's getting a little ugly in there, how I have to kind of make some things work, but I think it's still fine. Maybe at some point I will take all that information that's in there and turn it into its own little setup script that can work across different operating systems. Like similar to how you can install brew using like Perl and wget command, that kind of thing. I also updated I forgot to add this in as a bullet point, but I updated all of the docs in Getting Started to include the new information about how to get Clang Tidy installed. By having that there, when users go to do all this stuff, they should get Clang Tidy installed. So if you don't have Clang Tidy working, you can go through the steps and run through them again, and it should just work. I also updated the CMake utils file to appropriately find Clang Tidy. Before, all it did was try to find Clang Tidy, and that was it. But there's like Clang Tidy-17, Clang Tidy-18. There's a way to set it up such that it'll look for all of those variants and put a priority to which one you want it to find. In this case, we look for the highest version and then we go down. I tried to get Windows to work. It did not work. I don't know why the binaries seem to be corrupted. Like they just do not seem to function appropriately. So at some point I'll have to look into that, but I might consider disabling building and running tests on Windows. Building might be fine, but running the tests might be skipped on Windows, which is not really helpful. So we'll try to figure out a way to solve that problem. All right, so one of the sparkling new features or design patterns for 5.0 is replacing timeouts with IO waiter. And this actually means that like we would literally delete out timeouts. The timeouts we had for I2C would no longer exist, and other APIs that would take timeouts would go away as well. If you need to if you need to tell time, you can use a delay. I'm sorry, a steady clock. If you want to sleep, we might introduce a sleep class or a sleep interface that allows you to sleep the system. But there are a lot of other ways to kind of tell time or to be able to make things fail when deadlines are not met. I'll go into in a sec. So the two concepts here are timeout, which is a callback function, and it exists as a means to inject code while drivers are waiting for I/O to happen. So the idea is that you create a function, and that function knows when a deadline is over, and that could mean anything. It could be when a interrupt gets fired, and then sets a boolean some way. It could be when when a pin goes from low to high. So whenever you call the function, if it detects that the pin has gone from low to high, that might mean that its time is up. Some external source decides that. It could just be a timer of sorts. But basically, the point was, if something goes wrong, you should throw an exception to say that the deadline has been violated. The beauty of timeouts was that you could have just one, and then as you pass it around, you'd have this same time. You just have the same amount of time to do all the work. So no matter where, you wouldn't have to do any sort of math to say, all right, well, we spent 1 second out of the 5 seconds. Let me give 4 seconds to this driver. Then that driver finishes. All right, well, how much time do you have left? All right, you only have like 3 seconds left. All right, let's give 3 seconds to the next driver, that kind of thing. So timeouts were meant to make that a little easier. I/O waiter exists as a means to inject code while drivers are waiting for I/O. The difference between this and the other interface is that it has more control. Now the problem here is that timeout functions and I/O waiters don't really fit. They kind of fit the same niche, but don't play nicely with each other, and also don't play nicely. Timeouts don't really play nicely with a lot of things. So here's my first example. If an I/O waiter puts the system to sleep, because that could be something that it wants to do, how would timeout be pulled? You'd basically be stuck forever. If you were supposed to time out for let's say 1 second, and you get put to sleep, but there's no interrupt to wake you up every half a second or something like that, you won't ever wake back up. Therefore, the timeout will never hit. Therefore, you'll never call it. You'll never realize that time has run out, and now you're stuck forever. So that doesn't really work out very well. The second example is timeouts do not play well with with context switches and DMA, because the thread of execution is put to sleep. Because the thread of execution could be put to sleep until DMA finishes. So the thing here is that you could be let's say you have some thread and your IO wait basically tells you to context switch to something else and wait until the DMA is finished before you move back. There's no way to pull the timeout. You'd have to have some other thread handle the timeout for you and then wake up your task. But all of that could be handled with just using an IO waiter on its own. So the idea is that you'd have an IO waiter, you'd inject this into your drivers at construction, and this would give you a flexible enough API to be able to do different things. So here is one example. I feel like I've shown this at some point, but maybe I haven't. Maybe I'm just showing this at the people. Ignore the fact that these should have references in front of them, that this is a typo. But yeah, the whole idea here is that we have some function that performs some work. One concept that I've been thinking about is that you could have an IO waiter per thread. So that could be a specific type of thread, like you have a free RTOS IO waiter, so you could grab that instance of that thing and then pass that around. So let's say you have some way to grab the thread's IO waiter. And let's assume that every single driver that you constructed that is used on this thread uses that same IO waiter. Coordinating that I haven't figured out a way to make that smooth, but let's just assume that that's all figured out. So the idea here is that we grab the thread IO waiter. First thing we do is we take the timer that we've been passed. We schedule some time, and I forgot to put the time in here. It's supposed to be 5 seconds, so apologies there. Another typo. We schedule some time. We say, all right, I want you to schedule this callback to execute after, let's say, 5 seconds. And what happens is it sets up the thread waiter on its next wait to throw a HAL timeout. This basically says that the deadline has been exceeded. We want to set up the next time you call wait to call this function to throw. We want to basically make waiting on the IO waiter a throwing operation. And then what you do to ensure that the thread of execution is resumed, you can hit thread waiter.resume. So this all happens within a interrupt context. This particular API here is just a copy. It doesn't throw anything, so this is a perfectly safe operation to do in this context. It should be relatively fast. And this operation should be able to tell the operating system, hey, this particular thread is no longer blocked. You should give it some time. The moment the operating system gives it time and the inner driver does its work and then checks and then calls the wait function, it'll call our operation here. It'll throw an exception. No matter how deep this is, it's going to burrow its way through until eventually it finds a catch. And let's assume that the latest or topmost catch is this one. Now we can handle the deadline violation at this point. So that's the idea, is that if you needed to do an operation and you needed to jump out of it, IOWaiter just gives you way more flexibility and way more control. And I think that it's the right choice. The only thing I'm kind of concerned about is the ensuring that you've paired the appropriate drivers with the appropriate IOWaiter. And I guess before I move any further, one thing I want to say is I have considered the idea of I2C, timer, or other interfaces having an API to return back a IOWaiter. We just kind of make assumptions that some of these interfaces may have an IO wait type functionality. Therefore, maybe they return like an optional IOWaiter reference or something like that. I don't really like that idea because it feels too bottom. It feels too much like we're creating a framework, and we are to some degree making a framework, but I don't like the dependency, how we attach it to each one of the different drivers. I find that would be a bit of an annoyance to work with. And I like the idea of dependencies being passed from kind of a top level application view downwards, and less of an opportunistic API where some driver may or may not have this thing that you could utilize. In a way, I think that would make it harder to reason about whether or not you have those facilities available to you. And then also forcing this on everyone then makes it such that all objects have to have an IOWaiter. Some of them might not even need one. I think it just would be a bad idea. So moving on. How SPI channels. So before I said the thing I had brought up was combining configure with transfer, and I spent some time after writing the education page for SPI, or basically the user guide. I'm going to change education to user guide because I think education is the wrong term for this. I wanted this originally to be class material, but it's really just turning into how to use the new libhal APIs. Anyway, I've changed the semantics deeply when it comes to SPI. I also changed the way that I view what an SPI channel could be. So we're going to do a quick little skim through the education channel, or the education page. Zoom in a little bit. So there's a Understanding SPI by Roden Schwartz, and I love this video. It's all their videos that they do on like communication protocols are really well and really high quality. I think it's great just to rummage through all of them, just as like a primer, just to remind yourself how these things work. It's great. So the same little interface you saw before is there. I'm kind of just going to go over a couple of the bits. So settings here. There used to be a CPOL, CFA, or CPHA, or clock phase and clock polarity type modes here. Pretty much most systems will just use a mode number, and each one of those would just be bits. So and most of them just use the standard like what 0 to 3 means, which is like a certain type of polarity and phase and stuff like that. Not super important to describe here, but basically I decided to just merge those 2 bytes into a single byte. So now we have a 32-bit clock rate and then a UAT8 mode. And again, I think I talked about this last time, but we're moving all of the clock rates from floats to UAT32s just because fractional frequencies are not really useful in most of the embedded interfaces that we're building. In some other ones, it'll probably be reasonable to have fractional hertz, but not for what these are doing. Some interesting changes. So from what we had before, configure does something slightly different. Configure before would immediately apply the SPI settings to the bus. And from now on, I want everyone to think about SPI as being a little bit more protective of its resources. It has to do this internally because I realized that the previous design of having these random chip select output pins and a single shared SPI bus is that it's really difficult to try to use the interfaces alone to manage resource access. Um, I found that it was getting kind of complicated as I was able to build out like a object that you could pass output pins into, and then you could pass those. They then generate their own output pins. You could then pass those output pins that are generated into your SPI drivers, and they would always ensure that whenever you tried to do chip select, it would like prevent the other ones from chip selecting, which is kind of cool, but also problematic if the SPI is allowed to communicate as well. So I had to kind of couple those together. Overall, trying to ensure sole ownership and control at a time for SPI was becoming a little bit difficult. Actually, was becoming a little bit infeasible. So I decided to change the design into this channel idea. So configure stuff, but what it does, it actually caches the settings into itself, and then only when a transfer or a chip select is invoked will ownership of the bus be acquired, and then from there will the configurations be applied. So then any operations you do while you have control over the bus are kept underneath the settings. And then once you release the bus, something else could change the settings to what they need. This way, every single driver can just change the SPI rate to whatever the frequency they need, and that should just simply work. For very specific and rare and uncommon interfaces that require knowing the clock rate of the SPI, we provide a clock rate function. The one driver that I can imagine that needs this would be the NeoPixel driver. We use SPI as our way to generate the signals of ones and zeros to control the LEDs. But we need the clock rate to be very specific. I think it's like 4 megahertz. So that's the thing. Next up, transfer. I kind of talked about it before, but the idea is that anytime you try to call transfer or chip select, some sort of lock mechanism will attempt to acquire that particular bus and go from there. We're going to default to using an atomic lock. If you're doing single-threaded stuff, the atomic lock should be very, very minimal cost. It just kind of checks at the start that you have ownership and then goes from there. The idea is that other drivers would be halted, but if you're only single-threaded, you should never actually be in a situation where you can't access the bus at any particular time. So that cost should be very minimal. And then if you are using an operating system, that SPI object that you're using, you should pass it the appropriate operating system lock mechanism. All that to say is that whenever transfer is used, it basically acquires the bus and applies the configuration settings. And if you ever call chip select with true, it will acquire the bus until you call chip select false. And that means you can do multiple transfers in between without having to do the reacquisition thing. Keeps everything such that you can do a full transaction over to a device and then get out of it. Because we all understand that we have RAII and C++ for a reason. We have destructors for a reason. Remembering to chip select and then to turn off is difficult, especially when you have exceptions that can be thrown. So a bit of a weird thing I don't usually do, but I did add a couple of additional functions to the interface in order to implement the basic lockable requirement in C++. So if I go over to some of the code, you can kind of see what's happening here. I'll go over what the lockable thing means in a sec. Actually, I should just explain that now. There's some code here where I use this thing called a lock guard. Because the SPI has a lock and unlock, it's basically treated like a mutex. So you can throw that into lock guard and it will call the lock function, and then when it destructs, it'll call the unlock function. That'll allow you to perform SPI transactions in a scope, and that handles also the chip selects as well. So in this example, we'll kind of just go over it. So here we get some sort of SPI channel. We don't know where it came from, but we have one. We want for the entire rest of this function to basically lock down this chip select this device. Get ready to start talking to this device. So now we have access to the bus and to that device. We have a array of a single byte. That's going to be our we're going to write this particular byte to the device. So we do a transfer here. Next up, we're going to read back some data. So from here, we're going to do a transfer. We're going to put in an empty span, an empty array for the first parameter to say, hey, we're not writing anything. We just want to read back data back to this buffer, read it back. And now we can concatenate the values together, maybe divide it by some value, and then that'll give you the temperature in Celsius. And this returns back a float. I should have static cast this thing to a float, but you get the idea. So that's pretty much the big and difference here. The idea is that when you actually go to create an SPI object, and I have a couple of things of how to use like the different utilities and all of that here. Where is, yeah, device SPI device manager. So the code will look like something like this if you were to do it for like the STM. This doesn't exist at the moment, but this is something that I plan to implement so that this would be usable code. First, you create your output pins for all your chip selects based on whatever pins are mapped to that. Then you would pass, you create your SPI manager, you'd specify which port you want to use, and then also give it a bus lock. In this case, we can use an atomic lock. I might even default this to an atomic lock just because that's a pretty, I don't know if I can do that actually, but you get the idea. So we have an atomic lock for accessing the bus. If we want to acquire a channel, we can actually create an unlimited number of them. There's no particular reason that we would be limited to that. So when we do acquire a channel, we pass in a chip select, and that gives us back a SPI channel that is bound to the lifetime of this chip select, meaning that like if this guy dies, this thing is going to try to use that memory and it's going to mess up. And if I had a magic wand and had this particular feature in C++, I would add for acquire channel a attribute that says invalidate dereferencing, basically meaning that you can prevent this particular object from being used outside of the control of this object. That's not what that particular feature is meant for, but you could abuse it to make it that way, which would be really cool. But so the idea here is that this creates another object, a full concrete object that has access to this chip select and also has information about the SPI manager. Oh yeah, the SPI channel is also bound to the lifetime of the SPI manager. So if this guy dies, then this thing can't actually function. But this, by having access to the SPI manager and the output pin, it basically has the ability to access this particular lock, get the lock for itself, and then access the internal bits of the SPI manager in order to do the transactions, in order to chip select, do all that other stuff. So this thing kind of just scales on forever for as many output pins as you need. And you can have as many channel managers, and then you would give each one of these to each one of your different objects. So if this chip select is for an SD card and this chip select is for a display, you would make sure, maybe you'd even call it that chip select SD card chip select display. And this would be SPI channel chip select, SD card. And this would be SPI channel display. And you'd make sure that you map those to the appropriate objects so that they'd work appropriately. That's pretty much how SPI will look like, probably very close into the future. I'm actually working on getting SPI channel into libhal sooner than later, just because I want to start testing with it and working with it. And then once I think that it's in a solid spot, then we would make the transition to deprecate and even remove the current SPI. All right, let's move on over. So ADC 16, 24, 32, and DAC 16. So basically, talked about this last week, I believe, but I'm separating ADCs into their own resolution buckets. And actually, I'm going to do one quick thing. Did I not talk about this before? Yeah, okay, I just talked about using these new aliases. Yeah, all right, so I didn't actually talk about it much. But I did talk about using U16 and I16 for proportions, and this is where it's going to be used. So here, ADC 16 will always return back a number that is a full scale value from 0 to max 16-bit. The way this is done is by using a thing called I'm forgetting the word for it. I kept using it all the time, and it's inside the docs. It should be in the docs, but it's called upscaling, bit upscaling. Basically, if you take an 8-bit number and you duplicate its bits to its lower, to a lower least significant byte of a 16-bit number. If you go from 0 all the way up to your maximum number of 255, you will go in discrete steps between 0 and 2 to the 16. with only 8 bits of the resolution between each step. So it allows you to represent all possible like resolution values of a 16-bit number within a lower resolution number. That's all to say that you can get a really well-defined value out of this thing, similar to how we were using floats to give you a generic number between 0 to 1 for from most smallest to maximum. Here we have a uint16 for that. Now, ADCs between 4 bits to 16 bits are basically the most common, so I made a single bucket for this. I didn't see a use case that anyone would ever choose an ADC 8. 16-bit, like 10, 9, like 9, 10, and up to like 12-bit are super common. So common that making an 8-bit one just doesn't really make sense. I think even with 8-bit ones, duplicating the bits is a very short operation. So I don't see a use case for anything below 16-bit, so we have ADC 16. But I do see a use case for why ADC 14 should exist, or 24 should exist, purely because this is a lot of precision, and a particular driver demanding this particular ADC probably means business and needs that specific precision. So you should give it something as such. 32 is also in that realm as well, very out there. If a driver's asking for that, it probably needs it. So I can see distinctions between, well, we have the trade-offs of using this, or we have the trade-offs using this, or we have the trade-offs of using this. And DAC 16 just operates the same way. The full scale value for maximum voltage would be 2 to the 16 minus 1. And then for minimum 0 would be just 0. All right, so we've gone over quite a few things. The next one is that PWM is going to get split up into 2 interfaces. A lot of splitting that's happening right now. Just because I'm realizing that a single interface is difficult to manage for something that represents multiple separate useful modules. So we're breaking up PWM into PWM group frequency and PWM duty cycle 16. And yeah, we're labeling all of the different types based on the resolutions, because I think that's a useful thing to see in the type to know what you're dealing with, and what a driver particularly needs in terms of resolution. Now, PWM group frequency represents a group of PWM channels and provides frequency control for all of them. The kind of an example of that is that this particular device right here, I forget the name, PCA something or other. It is an I2C to PWM generator. It has, I put 16, 16 and I believe 12. I forget how many bit the channels were. I believe it was 12, but I kind of pulled that out of my butt. Actually, no, it is. It says right here, 16 by 12 bit. Yeah. So yeah, 16 by 12 bit channels, and it only has one source frequency. So if you were trying to control both a brushed motor and you wanted that to operate at, let's say, 20 to like maybe 25 hertz or kilohertz in order to operate the PWM cycles, which would be nice and smooth. But then you also wanted to talk to a server that operated at 50 hertz, you couldn't do that. It wouldn't work. So the idea of PWM channels is that it doesn't have control over the frequency, because giving it that kind of power would be too much. It only has control over its duty cycle. So you could pass those on to different devices, and then those different device drivers could ask for what the frequency is to see if it's within a range that's acceptable. On the opposite side, we have frequency group, which allows you to control the frequency of a PWM. Now, I expect that in a lot of cases, PWM group frequency isn't going to be passed to drivers very often, because it's a bit of a high responsibility object. By giving this to a driver, it means that you are allowing this particular driver to have full control over the frequency, and that means that the duty cycles that you have could be problematic. Now, if you only have one frequency source and only one PWM duty cycle, if you only passed one of those or one of those to another driver, made no other duty cycle objects, that is perfectly sound and safe. And when we make 2 and pass it to some other driver that has other requirements, all bets are off. So how we manage that, maybe as a description of how things ought to be done, but I'm still thinking about if there's any clever ways to ensure that people don't shoot themselves in the foot. I will say, if there was some way to map that certain objects relate to each other very strongly and can only when I pass something of this type to something else, I want them to kind of say, like, oh, these things belong to each other. These things are grouped, and like these are, sibling objects of each other. Therefore, we want to make sure these are the same, they come from the same object, versus potentially having a frequency group from a very different PWM object and a duty cycle from a other different object. So just a thought. All right, so hopefully we can wrap this up because I think this is the last thing we're going to go over. The new CAN interfaces. So CAN is also getting broken up into its component parts. Trying to put everything into a single interface was putting in way too much responsibility in one place. So now it's broken up into 5, or technically more than that, but I'll go into it. So for sending and receiving messages, we have CAN transceiver. You have the ability to when this is probably the most common object that will be passed to other drivers. So the RMD motors, the smart motors that we use that talk over CAN, we would pass a CAN transceiver over to it, and probably also a filter, but we'll go over what filters are like later. But this is what it would use to send messages, as well as also receive them using the receive buffer and receive cursor. I don't remember if I went over in detail how the receive buffer and receive cursor worked in the last meeting, but just a short recap. Receive buffer is operated like a circular buffer, and the receive cursor tells you where the current write index is. You can use that to track it as it moves over in order to see if any new messages have come in. If you aren't interested in actually using a receive buffer but want to get an interrupt on every single message that occurs, you can also use the CAN message interrupt. The hope is that if you were to spawn 2 of these, like if you were to ask for the from the device manager, I say, hey, give me a CAN transceiver and also give me a CAN message interrupt. It would support both the DMA, or not DMA. It would support moving items that come in over interrupts to the receive buffer, but then also call your on-receive handler if you placed one there. So both should be well supported. And I guess one little thing to add in is that I looked into quite a few different devices from STM to NXP to I think I looked up one more. It might have been TI. I looked up all those. I looked up quite a few different devices, and none of them supported DMA. Almost all the CAN devices work through interrupts, which actually makes life a lot easier because it means that making the circular buffer is really trivial. So that's the thing. All right. So I also removed the bus configuration stuff. This kind of limits the kind of stuff that CAN transceiver and CAN message interrupt can do. So things like changing the baud rate, changing the filter mode acceptance, the filter mode, and then also changing the bus off handler as well as turning the system back on. These are all things that I think the application should manage, or some part of the application should manage specifically. But this is not a shareable type thing. There's no reason for all of the RMD objects to kind of be exposed to these APIs. I'm not trying to gatekeep too much in terms of how we design our APIs, but I also think that it makes sense to just not clutter CAN transceiver with all of this extra stuff. And finally, I spent a lot of time thinking about how we could do filters. I bet this seems obvious, but I originally disliked the idea of having separate interfaces for the filters. I was really looking for a way to make the filters all work with the original CAN interface. And then once I broke that desire, making this work actually became quite easy. The idea is that we already know that the number of resources in a CAN peripheral are going to vary. The types of interfaces, the types of filters are different, but not only that, but how they represent them and how many they have and how many they're capable of generating or having in general is very variable. And it's not really known unless someone looks at the data sheet and kind of figures it out. Although it can be known at runtime when you've tried to access all of the things that you need and then you throw an exception because you ran out of filters or resources to generate these filters. So that would be one of the responsibilities of the CAN driver, would be that the filters, whenever you create one or acquire one, it has to check to see if it has the resources for that. And if it does not, it throws an exception. And in here we have these allow functions. Basically what they do is you pass in an ID and it'll allow that ID through. If you pass in null opt, it disengages the filter, meaning that if you pass in an ID, that particular ID will make it through the filter. If you put in null opt, that filter basically becomes deactivated and the messages you were previously getting no longer come in. The most common interfaces or filters were identifier, so single ID, mask, and range. So we're just going to support those. And if a desire and need comes into the future for another more generic or another generic interface, then we can also add that in as well. This is already a design pattern that we're going to utilize for USB. It made a lot more sense in USB initially just because uh, endpoint count on devices is always variable. It's kind of just one of those flexible things about USB. And I knew that we could never, it would make for a really bad experience, I believe, if we had everything kind of mapped into a single interface. So breaking up CAN, I think, also gives us a lot more flexibility and makes the code a little bit more safe in a lot of ways. And that's about it. Thank you for coming to this meeting.